I'm going to give you an easy example. Let's say you have a box, okay? And I'm going to give you a bag of atoms. So a bag that's filled with atoms. And if I were to ask you to throw these atoms into this box, what would you expect to see? Well, what you're going to see is that all of those atoms are going to pack up very nicely. And as those atoms are picking up, they're going to follow a certain pattern. Now, a scenario called close packing occurs, which is basically the tightly packed composition of these crystal structures that you can expect to see. So those spheres are going to be arranged so as to minimize the unfilled space, right? So if you're going to fill it up and wait patiently, what you're going to observe is something like this. Very beautiful. So you're going to have places where atoms are closely packed and places where there's nothing, basically called vacancies, right? Unfilled space. And you're also going to have grain boundaries, these white like lines that you're seeing over here, where the atoms didn't really align perfectly. And all of these defects are things that you see when trying to form or combine crystals. So there are a bunch of structures that we're going to study. The first one that we're going to start off with is simple cubic structure. Why? Because it's the simplest, as the name implies. So if you throw those atoms inside that box, keep that in mind. What you're going to see is this beautiful structure over here. What are you looking at? Well, basically, 8 atoms are going to come together in this specific format. And if you're going to take 4 atoms, so these specific atoms over here, this is what you're going to see, right? And to visualize these atoms a little bit better, so if you look here, this is made by York Physics. These are very good illustrations to help you better understand these models. So what you're seeing is this specifically. So those 4 atoms are going to join together like so. Okay, very simple. Now, we want to introduce a very unique concept called unit cells. Okay, so I'm going to put this down here and I'm going to explain what that is. A unit cell is basically a repeating unit in structures. So like a cell is basically a box, but in some cases it's not going to be a box. So we're going to explain those cases where it's like a little hexagonal volume. We're going to explain those cases, don't be worried. So a unit cell for most of these structures is going to be something like this, a little big cell. And if you're going to take this and basically take the vertices, the corners of this cube to be the center of each of these spheres, so something like this, you're going to form a lot of repeating cubes like this. Okay, so what we're doing is we're connecting these centers over here together like so and creating this cube. Okay, so if you do that and you slice everything up, you're going to make this resulting structure. Again, Sketchfab is always the best for visualizing these things. You're going to make this beautiful structure over here. So what we've done is effectively removed all of the other atoms that were present over here. So we're left with these parts. This is basically like 1/8 of the whole sphere. I'm going to explain what that means in a second, but this is the resultant thing that you're gonna see. Okay, so if you do that, you're gonna see something like this. So this is how your atoms are gonna combine within your unit cell. And I said it's 1/8 because if you look at a cell like this, we're looking at this piece over here. So if you were to cut your cell first up in half this way, right, like this way, then cut it again this way, then cut it again this way, you're going to form 8 pieces. You can try this with an orange, cut it in half, cut that half in half, cut the half you form in half. You can basically make 8 pieces. So 1, 2, 3, 4, 5, 6, 7, 8. So 1/8 is basically what this is going to be. So this is 1/8 of an atom. So this is very important. We're going to return to this in a little bit. So we said that a unit cell is basically a repeating structure. So what you're going to see is effectively this repeating over and over again. So for simple cubic structure, when asked to draw it in an exam, it's very important to start off by drawing a little square, like so, drawing another square on top, like so, doing this and doing this, and then putting atoms at these corners. So that's effectively what a simple cubic structure is. So there's basically one atom in this structure. like within the unit cell. Okay, what I mean by this is if you come here, I said this is 1/8 of an atom. So there are 4 of those, right? On top, 1, 2, 3, 4. So 1/8. So on top is basically 1/8 times 4, which is 1/2. So 1/2 of an atom is basically on top. And then if you look at this bottom thing over here, at the bottom here, you also have 1/2 of an atom. So together they make 1 atom. So basically 1 atom is roughly contained within each unit cell. So that's something that's quite important for you to think about. We're going to introduce 2 new concepts that are quite important. The first one is lattice parameters. Okay, a lattice parameter basically refers to dimensions that we give to this unit cell. So the length, the width, the height, which is all the same because it's a cube, is what we call A, and that's a lattice parameter. It's just a parameter that we give to this lattice. It's important for you to just think about that, right? So that's a lattice parameter. So I just basically drew it like this. So I've like moved them apart so that it's clearer. So if you can see this, like the spheres are still the same. I've just like moved them apart so that they're much visible. Okay, so this is what we're going to call a lattice parameter. So we're going to derive like very important things with this lattice parameter. We're going to relate the center of these atoms to this lattice parameter, or the bond length to this lattice parameter. Another important thing that we're going to introduce is what we call the atomic packing factor. Okay, how packed are this thing? So I'm going to call this the APF. So it's basically the ratio of the volume of atoms, right? How much volume do those atoms occupy, divided by the volume of the cell, right? So basically, what is the total volume of the atoms divided by the volume of the cell? And to memorize this, keep this in mind. At the top, we have A. At the bottom, we have C, like the alphabet, A, B, C. So A comes first, atoms on top, and then cells at the bottom. So this is what we call the atomic packing factor. So questions can ask you to find the atomic packing factor for each of all these different structures that we're going to talk about. So we're going to start off with that. The first thing that we need is the volume of the atom. So the volume of atoms in simple cubic. Okay, so a sphere, basically, the volume for a sphere is 4/3 pi r cubed. Is basically the volume that you use, or the equation that you use rather, to find the volume of a sphere. Okay, so I'm very bad at drawing spheres, so I'm just going to say this circle is a sphere. So, like I said, we basically have one sphere, right, inside of this unit cell. So the volume of atoms within the unit cell, right, which is 4/3 pi r cubed, is basically, so the volume of atoms, I'm going to call this VA, is basically just 1 times 4/3 pi r cubed, okay, of the cell itself as a whole, right? The cell is basically a cell, as you would know. It's a cube, like so. It basically has this parameter A, which is over here. So its volume for VC is basically A cubed. Most of these cases, you're going to end up with volume of atoms in terms of R, and you're going to end up with volume of cells in terms of A. And you want to find the relationship between A and R for every scenario. If you were to look at this, this is the radius, okay? If you look at this, this is the center, remember? And these tips are touching. So this is the radius R over here. The radius of a sphere, right? Because the radius of a sphere is basically the distance from the center to one of the corners. There's also the radius R, which is over here. So basically 2R is this distance over here. So it's very easy for you to say that for a simple cubic structure, A is equal to 2R, right? It's very simple and very straightforward. So that basically means that your atomic packing factor, which is the volume of that, which is 4 over 3 pi r cubed, divided by a cubed. In this case, because I know that a is equals to 2r, I can remove a and I put 2r. 2 cubed is basically 8, so I have 8r cubed. You can easily see that these cancel out, and if you divide these two, you're going to end up with 0.52. So this is what we call the atomic packing factor, meaning that 52% of this entire unit cell is made up of atoms. The rest is just vacancies, empty spaces. So this is quite a low packing density and not so nice, but it's an important structure that you can be asked to find. The next thing that you're going to look at is another type of structure. So again, remember, you are still just throwing atoms inside a different structure. One that can form is called body-centered cubic structure. So BCC for short. So BCC. Okay. The same logic, we're going to start off with the process of just throwing atoms. So what you're going to see is that the first atom is going to make up the first layer. So this is layer number 1. And then the next atom is going to come in but fill the middle. So these atoms, these like white atoms that you're seeing over here, are basically in between the same structure. So the same structure that you had in this one, but imagine that there's a white one now in the middle. Okay, so these layers are just basically coming in between all 8 atoms, and then that's layer number 2. Then layer number 3 is same to layer number 1. Then layer number 4, layer number 5. So the same manner, we can extract a simple cube, and we can just focus on the same layout, the same number of atoms like we did. We just take 8 atoms in total, and we're going to have this, and the 9th atom is going to be in the center. So you can see that these 2 atoms are not touching each other. That's very important. And 4 atoms are on top over here. 4 atoms are on the bottom over there. Okay, so the same process. To easily visualize this, I'm going to show you a little visualization on Sketch Fab. This is effectively what we call a BCC, body-centered structure. So why is it body-centered structure? Because, well, we have one body, one atom, which is centered in the middle. So similar to simple structure, we have 1, 2, 3, 4 atoms on top, 1, 2, 3, 4 atoms on the bottom, and 1 atom in the middle over there. Okay, so you can see that these 2 atoms are not touching each other. These 2 atoms are not touching each other, but these atoms are, right? So you can see that this atom is touching this central atom over here, and then touching this other atom. So the diagonals are touching. This diagonal is touching, this diagonal is touching, this diagonal is touching. So the diagonals are touching, but the atoms on top and the atoms on bottom are not touching each other. So that's important for you to think about. And in the similar manner as we did, we can extract a unit cell from this as well, cut all of the top parts, and only be left with the simplest structure that we can form. So if we were to slice everything up, from York Physics again, very nice, we're going to remove, again, remember, we're going to remove everything except 1/8 of the cell, similar to simple cubic. If you've understood simple cubic, this will be quite straightforward. So this is like simple cubic, but with 1 atom now in the middle. I think you can basically guess how many atoms are in this one, right? So number of atoms in BCC. So effectively, this is 1/8 by 4 on top. That's going to be 1/2. Then 1/8 on the bottom. That's going to be 1/2. So 1 cell in total. Plus this big fella over here, 1. So in total, we're going to have 2 atoms, which is quite important. Okay. And then the sketch for an examination situation, questions might ask you, can you sketch a BCC? Again, start simply with a big cube. Then just place atoms at every corner over there. Okay. And then just place 1 atom in the center over here. Right. And just show that, this is the atom that's in the center. This should suffice for BCC. Okay. Similar to simple cubic, we're going to talk about the atomic packing factor. And remember what I said, it's basically A on top, alphabet A comes first. So volume of atoms divided by volume of cell. Again, the lattice parameter is basically something that we came up with. It's a parameter that describes this cube that we came up with, and we're going to call that A. And you can sort of figure out that we have two atoms, like what we said, right? And 2 times the volume of a sphere, 4 over 3 pi r cubed. The volume of this whole cell is A cubed. Okay, so again, the next logical question is to ask, well, what is the relationship, sir, between A and R? The next simple logical relationship that you can establish. But there's a problem. This is not similar to simple cubic. For this fact, these two atoms are not touching. Okay, so this atom and this atom are not touching. So you can't say A, which is from this corner to that corner, A is basically equivalent to 2R. We can't do that because this radius is not touching. There's this gap over here. But you can realize something very fun and interesting is that the diagonals, however, so if you were to start from this corner, run through to the other corner, they're basically going to touch. So this center pass through this atom and arrive at the other corner, they're basically going to touch. So that's something that's quite important in that for a sphere, so I'm going to show that for a sphere that is something like this, this diagonal over here is going to touch this other diagonal over here, and they're going to be atoms all the way through from this corner to that other corner. So you're basically trying to find the length of the cross diagonal for a cube. Basically, what is the length of that cross diagonal for a cube? If this is atom number 1, remember that this corner is touching this other corner over here, right? If you don't remember, this corner over here is running through the center and touching this other corner on the opposite end. So it's going to touch this corner over here on side number 2. So how can we get from 1 to 2, right? You can go here, then here, then here, then arrive there, right? But I can also arrive at 2 using a triangle. So if I move down like this, okay, and I arrive at this position, this is my lattice parameter A. I can then move diagonally like this, okay, that's D. Then I arrive at point number 2. And what I basically want to find is the length of this diagonal over here. So it's a very simple triangle that I can extract. So let's say this is 3. So extracting that, you can basically do this and say this is 1, this is 2, this is 3. Okay, so you know that this is A, and then you want to find the length of D. This is simple Pythagoras. So this length is A over here. This length is A over here. So what is the length of the hypotenuse? Remember, this is 90 degrees, guys. So what is the length of the hypotenuse? So D is equal to A squared plus A squared, the square root. So it's basically root 2A. Okay, so D is root 2A, which is 3, 2. 3, 2 is root 2A. This is basically A. So you want to find what the length of 1, 2 is, basically this hypotenuse. Okay, so what you're going to do is basically say the hypotenuse is equal to the square root of root 2A squared plus A squared, which is root 3A. Okay, so this is basically the length of this hypotenuse. But remember that there were 3, so we're basically going from the center of one atom to the end of that atom, and then the big atom was in the middle, and then the last atom was on this side. So we had R over here, which is the radius for one of the spheres. Then we have 2R which is the big sphere in the middle, because like its diameter is along the diagonal, so that's 2r. Then we have r at the bottom over here. So you can basically see that 4r, which is the hypotenuse, is also, so the hypotenuse is also equal to 4r. So in this case, 4r is equal to root 3a. There's a very good observation that I've just made here, because I can therefore say that a is equal to 4 over root 3r. Okay, so that means my atomic pecking factor will basically be equal to 2 times 4 over 3 pi r cubed divided by a cubed again. So a is 4 root 3 now, cubed r cubed, 0.68. Right, sorry, 68% of the entire unit cell is basically occupied by atoms, right? So 68% is occupied. Okay, so face-centered cubic is the same. Now with face-centered cubic, the structure is a little bit more complicated, but it's very easy. You have 4 atoms at the corner. Again, always 4 atoms at the corner, guys. And then you have an atom at every single face. Right? So we're going to extract this. It's much easier to see if you extract. This is quite complicated. So you have 4 atoms, atom number 1, atom number 2, atom number 3, atom number 4, 5, 6, 7, 8, and then an atom at every single face. So an atom on this top face, like it's resting on that top face, an atom on this face, an atom on the face down, an atom on this face, an atom on that face, an atom on that face. And we can slice it up again, cut it like so, cut it like so, cut it like so. And what you're going to make is basically a structure like this. So similar thing, there's always 1/8 at every corner, and you're going to slice. So there's an entire atom over here. You're going to slice it up, and there's going to be 1/2 of that atom inside. So this is 1/2 of an atom, 1/2 of an atom, and you're going to slice it up, right? Okay, so this is what I'm talking about. Okay, so this is what I'm talking about. You've basically sliced the atom open. You've basically sliced it up like so. And yeah, it's very straightforward to see that you have 1 atom, 4 atoms on the top, like as usual, as per usual. You have 4 atoms on the top, and then you had an entire atom that was occupying this top part, but like it was sliced, like the entire atom was extruding outwards, but it was sliced. So you have half of the atom now inside, the other half is gone. This is nice because you can see that like from this corner all the way to this corner, like it's very perfect, right? We can easily find the parameter a. Like I can easily see that this is r, this is 2r, this is r. Like it's the outer diagonal. It's no longer the like this cross diagonal that we had in BCC. So FCC is going to be in walk in the park. Okay. So we're going to start off as per usual. I think you can basically guess where this is going. We can start off with number of atoms. Now, as usual, we have 1/8 at the top times 4, 1/2, 1/8 times 4, 1/2. Then we have 1/2 of this big guy on this face. So 1/2 there, 1/2 there, 1/2 on this side, 1/2 at the bottom, right? So another half on this other side, another half on the back. So it's 1 atom, 1 atom in this way, right? So basically 1 atom in this way, another atom in this way, another atom in this way. So it's 1, 2, 3, right? 3 full atoms, like 1, 2, 3. Okay, so 3 atoms. So 6 halves, right? Which is basically equal to 3 atoms. Those blue ones. Okay, so the total number of atoms for FCC is equal to 4 atoms. And now you can probably guess, we're going to talk about the atomic pecking factor, the volume of the atoms divided by the volume of the cell, which is basically now 4 times 4/3 pi r cubed divided by a cubed. Okay, so now we're going to talk about the relationship between between A and R. So basically the relationship between A and R, which is this A that's over there, and the R that's, so this is the A as per usual. Okay, I forgot my exam sketch. So the exam sketch, if I asked to sketch this in an exam, start with like a big cube. Like, I'm very happy that I actually figured out how to draw these cubes. They used to like worry me for a little bit. So put the atoms over there, and you can just use another color, something like that, and then like show that there's an atom here at the top, show that there's an atom on the side, atom on that side, atom on that side, atom on the bottom, and an atom on that. So that's a simple sketch for FCC. Okay, the relationship between A and R is now straightforward because of that cross diagonal, right? So this diagonal over here, these atoms are touching, right? So that's very straightforward. What I mean by this is that we have one atom over here, number 1, crossing and meeting number 2. So this is A, that's 3, and this is A. So the cross diagonal in this case is not that complicated. It's not this one in BCC. It's basically that one for FCC. So basically the value of the diagonal, which is my hypotenuse. So the hypotenuse is equal to the square root of A squared plus A squared. So that's root 2A. We have R over here, 2R, and then R. So, and the hypotenuse is also equal to 4R. So 4R is equal to root 2A. Therefore, 4 over root 2, 4 over root 2R is equal to A. My atomic packing factor is effectively, my atomic packing factor is basically, okay, 4 times 4 over 3 pi R cubed over 4 root 2 cubed R cubed. Okay, then we cancel that. We calculate it and we end up with 0.74%, not percent. That's basically 74%. Okay, so we're getting better. We're getting better, more and more efficient. So you realize that 24% of the entire cell, rather, is occupied by atoms, which is quite good. One thing that I left out is basically distance between adjacent atom centers. Some questions can ask you for what is the distance between adjacent atom centers. In this case, you can realize that one atom center was over here, right, which was R, and then the other atom was in the middle, right, over here. The other center was like in the middle, which was like R. So the center, like centers between two atoms, was basically 2R, right, which was the distance, right, that I'm going to call D, between adjacent DC. I'm going to call DC between adjacent atom centers was basically like 2R. So if 4R is equals to root 2A, 2R is equals to like root 2 over 2A. The same can be said for like BCC. They can ask you for like distance between adjacent atom centers, and in this case, remember, it's the cross diagonal. In this case, that meets, so we had the cross diagonal of like 4R. So the centers will be like from here to here, which is 2R. So 2R, which is DC, is basically going to be equal to root 3 over 2A. So that's the distance between adjacent atom centers. And for simple structure, it's basically like, because these are touching in the center, so the distance between the centers is 2R, which is equal to A. So, which is equal to A. So those are some questions that they can ask you. And you might be wondering, why is this important? This is very important from an engineering perspective because let me give you a simple question. Like, let's say I give you copper and I tell you to find the density of copper, right? Or I can ask you to find lattice parameters, or like they can ask you weird questions. But let's say I've given you copper, right? And I've told you that let's say copper is like FCC. So copper basically has an FCC structure, right? And by now you should be like able to draw this from head, guys. The cross diagonal, the lattice parameter here is A for FCC. This is like touching, so the cross diagonal, like this one for FCC. So like another like trick that I like to remember this is that like the diagonal is across the face for FCC. So the diagonal is like across the face, and for BCC, the diagonal is through the body. So the diagonal here, like diagonal, is like through the body. It's like a little trick that I like to like distinguish between BCC and FCC, so that I know that the other one is like from one corner to another corner, so it's like √3, so it's longer, so that I don't have to like keep on doing calculations. So like here I know that now it's like √2, so √2a, which is that is basically gonna be like 4r, because there's gonna be 1 in the middle and like an r over here, so 4r. Okay, let's say I have these facts and I know them, right? I can give you copper and I tell you that the density of copper right, like I know this by head to be like 8,960 kilograms per cubic cube, m cubed. So that's the density of copper. You can do interesting, cool things with this, either to find this density. So I want you to think about this, right? Density is basically mass, right, divided by volume, right? So if you think about this, this is mass of atoms in unit cell, okay, divided by a volume of atoms in unit cell. So if you have a unit cell, how many mass is inside that, and what is the volume of atoms within that unit cell? That basically gives you density for any material. And this is a very important realization, because from this fact, let's say I know that, oh, for copper, FCC, there's 1, 2, 3, 4, 5. Okay, 1/8, half of that. Okay, so there's like 1 atom across the vertices. Okay, so half there. So they're like 3 atoms, so 4 atoms in total. So I know that they're going to be 4 atoms in total for face, right? Face, they're going to be 4 atoms. And then I'm going to multiply by the mass of 1 atom, which I know is AMU. That's 1.66 times 10 to the power of -27. So you're going to have the total mass of the atom. So I can give you like this and just say number of atoms, right? So I can give you like BCC. You should know that, oh, BCC is 1 atom in the center, 1 atom, so it is 2 atoms. Simple structure. Oh, it is 1 atom basically in it, right? So we build in complexity. 1 atom, 2 atom, 4 atom, right? So the volume of atoms within that cell is basically going to be what? 4 times 4/3 pi r cubed. So you can see that the situation can be quite tricky now, right? They can just give you this and ask you to find the density of the material, and they only give you the lattice parameter for a unit cell. So you know that you can find the value of r, because if you're given A, if this is given, you can calculate the value of r very simply, and you just plug it in here, and the mass, number of atoms, you know, find the density of the material, and you can confirm that indeed it is this. Or they can give you the density of copper, and they ask you to find the number of atoms. Or they can't really ask you that, but they can ask you to find the lattice parameter. So from the density of the material, if it's given, you can find the radius. If you can find the radius, you know this relationship, so you can find the value for the lattice parameter A. So this is for FCC, and you know that for BCC, it's like √3a is equal to 4r, right? And you know that for simple, 2r is equal to a. So you can like play around with this. If you just know this, for like these three different structures, you can find the value of R, the value of A, and basically get what you want. So this is like an application of this fact, like why we need to know this. This is something that we've just observed. In the next video, we're going to introduce the last two ones. I made that a separate video because they're quite complex and quite difficult to understand, but not so impossible. So we're going to look at diamond, cubic, and hexagonal. Diamond, cubic, and hexagonal closed peg structure next.